Good morning, welcome to our talk, 3D Virtio, a guest-to-host escapes on QEMU KVM Virtio device. We came from College of Cybersecurity, Jinan University, China. First, let me introduce myself. My English name is Matthew. I'm a graduate student of Jinan University. My supervisor is Professor Zhen Wong. I'm interested in virtualization security and IoT security. I'm enthusiastic about CTF and gaming as the former leaders of our university CTFD. As point, I just finished my intern at Tencent KVM. I participate in the team AOE in the DevCon CTF and we won the champion for this year. You can find me on Twitter with this ID. This is the agenda of our talk. I will first introduce some research background about QEMU and Virtio GPU. Then I will share some experience about building an effective buzzer for third-party library. This method is not limited to virtualization scenario. You can apply this design pattern and on any other targets. First, I will reveal how to exploit a heap overflow vulnerability and deliver a full guest-to-host exploit on parallel virtualization device. And last, I will show you a demo of our exploits and conclude the talk. So why do we choose QEMU as a research target? We noticed as cloud computing becoming a crucial business for many companies. Vendors are paying out great money on securing their virtualization products. Microsoft launched the Hyper-V bug bounty program, offering up to $250,000 for a guest-to-host escape exploits. And the VM category has become one of the most valuable targets on world-class hacking competition like Ponchon and Tenfu Cup. For example, in Tenfu Cup happens at last November, a QEMU KVM guest-to-host exploit was awarded $80,000. This encouraged many security researchers to put their energy on virtualization security research. Many great talks on this topic came out on top conference like Backhead, Offensive Coin, and Tencent. We believe this trade will last for a long time and we definitely want to join the party. We consider QEMU as a good starting point because it is open source and it has many similar designs with other virtualization products. Inspired by previous research, we found an interesting target, Virtio. Virtio is a parallel virtualized model to improve I/O performance. In traditional virtualization models, full emulation devices are widely used. The hypervisor will take care of hardware emulation and the guest machine has no clue about it is running in virtualization environments, so it doesn't need any modification on guest machine for this mode. Though full emulation is flexible, it suffers from poor performance. So parallel virtualization was proposed, and Virtio is the most popular standard of this kind. A dedicated driver will be installed on guest machine as front end, and QEMU provides an interface as backend. A ring buffer-based communication channel is set up between guest and host. When there's an I/O operation request on guest, it will forward to the host machine through Virtio channel, so that the host can use hardware resources to process the I/O requests. For now, many Virtio devices have been supported by QEMU. For example, there is Virtio Net PCI for networking, Virtio SCSI PCI for storage, Virtio Bloom for dynamic memory adjustment, Virtio GPU for graphic acceleration. Among all these devices, Virtio GPU intrigues us the most. It is an important attack surface discussed in the talk Dig into QEMU Security on CanSec West 2017 by GU316 Gerten. This module aims at accelerating 3D rendering performance for guest machine. If you want to play a 3D video game in the guest machine, you probably want to turn it on. A third-party library Virtio renderer is used in the backend. In short, Virtio GPU backend accepts graphic rendering commands from the guest machine and invokes Virtio renderer APIs to process them with hardware GPU computing advantage. Before hunting for bugs, we did some background research. We've seen the first public QEMU guest-to-host exploits on Backhack USA 2011. It utilized a vulnerability in PII export power management emulation code on QEMU. And many successful exploits came out during last decade, most of them targeted on full emulated devices. For example, the network emulated module called SLIT. There were 2 successful exploits for this module in last year. Vulnerabilities has also discovered in Virtio device, for example, CVE 2019-14835 in vHostNet kernel module. But there's no public exploit for it. When we first approached the source code of our Virtio renderer, we found there is already a fuzzer comes with the repository and probably running at somewhere. This is kind of disappointing because a well-written fuzzer kills bugs. That means we are less likely to fuzz out some good bugs. On the other hand, it is also a good opportunity. We can modify the fuzzer and save our time to build a new one from the ground up. So let's look at how the original fuzzer was implemented. It was based on libfuzzer, simply set up objects and feed mutated data to the target function. Then clean up the environment. This submit CMD function accepts port data, decoding, and perform corresponding commands. We compile the fuzzer and run it for a while. It turns out this original fuzzer is far from mature. Its efficiency is poor, the coverage goes very slow. Its coverage is poor. Even with sufficient time, large portion of code remain unexploited. So we dig into the code to see the reasons and see if we can improve it. The target function submit CMD will call this VRAM decode box function, which contains 45 subcomments. Each follows its own syntax. If the data does not follow the syntax, decoder will drop it, so random bit mutation does not work well. Most of mutated data are dropped, leading to the poor efficiency. The poor coverage can be attributed to 2 reasons. There are 24 commands exported as APIs. Many of them can be triggered from guest machine, but only this one function is taken into consider of fuzzing. Among 45 subcomments on last slides, there are some dependencies. For example, there is a command for creating objects, binding objects, destroy objects. Obviously, you cannot destroy an object before creating it. So submitting 1 command for each fuzzing iteration is not enough. To address these 2 problems, and in the hope of finding more bugs, we apply the idea of structure-aware fuzzing. Google has an elaborated document on this topic. Also, Nat Williamson from Project Zero presented a great talk on Authenticon in 2019. And we have Jonathan Maisman on Backhack USA 19 sharing some knowledge about these techniques. Many great bugs are found by these fuzzing techniques, so I highly recommend you to take a look at these materials. The idea of structure-aware fuzzing is simple. While traditional mutator generates arbitrary random bits for input samples, which mostly are discarded by the target function, we want to provide structured information for the mutator so it can mutate based on some rules, generating more valid samples. One of practical methods to apply structure-aware fuzzing is to use libprotobuf mutator library. It leverages protocol buffer language to define structured information. Let's see an example here. Say we want to fuzz one of the subcomments called Virtio renderer resource creates. We can locate the arguments it accepts and transfer them into the protocol buffer format. This is trivial. Simply giving the variable name with correct state type is enough. The libprotobuf mutator then reads from the protobuf definition and mutate the arguments based on it. Integrating this into the fuzzer is also easy. Libprotobuf mutator provides the convenience macro to help mutating over protobuf objects. We change the libfuzzer entry function with this, and its arguments is the protobuf object we have defined. As we mentioned before, we want to submit massive comments in one fuzzing iteration, now we call it accession. And we want to mutate not only the arguments of each comment, but also different combination of calling series. So we define a section object like this. It contains multiple comments, and each comment is a protobuf object, contains its own argument definition. For the setup and teardown, it remains to be exactly the same as the original fuzzer. But we change the invoking logic. The new version distributes comments according to its types. It extracts the mutated arguments and feeds them to corresponding API. And it is good to go. We first adapt a few comments to the fuzzer and get it runs. Meanwhile, we're adding more comments for it, and we can see the coverage increase much faster than the original fuzzers. Actually, it is becoming faster and faster as we adding more comments to it. We developed the fuzzer on a VM of VMware Workstation. It runs at around 30 executions per second. Then we deploy it on a desktop with Intel i5 7500 GTX 1080 Ti and get around 315 executions per second. This is because some commands are preceded with graphic rendering operation with bare metal GPU. These commands can be processed much faster. More than 300 executions per second sounds not bad, and it is for one thread. On our machine with 4-core 8-thread, it can have over 2K execution per second, but we want to get a decent bugs in limited time. Instead of waiting some bugs came out, we try to make it run faster. We use a tool called GPerform Tools. It is a performance analysis tool that's provided by Google. We linked the binary with GPerform Tools library so it can collect Performance data and generating code graph. The first command here will run our fuzzer for 60 seconds and generate Performance data called perf.out. The second command will generate a code graph based on the Performance data. You can see the complicated code graph on the right. Then we look at the code graph closely. The second line on this block indicates the execution time of this function over the whole running time. The last line on this block indicates the execution time of this function and its sub-function over the whole runtime. And we can see the VRAM renderer init. This initialization function occupies 61.7 of execution time, while the target function, Virtio renderer CMD, only occupies 0.9 of CPU time. If we want it run faster, we can reduce the VRAM renderer init calls or even eliminate them. So it saves time on initialization and can spend more time on the function that we're interested in. To do this, we look at the APIs provided by the target library and see one entry called Virtio renderer reset. In original fuzzer, we set up the renderer at each iteration and clean up at the end. Instead, we can set up just once and reset at the end. This saves massive operation of mallocs and frees. To enable this, we can replace the cleanup function with this reset one and move the initialization function to the global setup functions, which only executes in first iteration. It turned out this modification works surprisingly well. We finally get around 1,500 execution per second per code, which is about 5 times faster than the default fuzzer. The conclusion is that malloc and free operations are expensive, especially with the address sanitizer enabled. We can use the GPerform tool to identify time-consuming function and try to replace it with something else. Finally, we can run this fuzzer confidently. The first bug came out in less than 30 minutes, and the one we used in exploit found in 48 hours. So let's see what we got from the fuzzer. We found a couple of serious bugs, but due to the limits of time, I will only show 2 typical ones here. The first is a null pointer dereference vulnerability. It happens at the create sampler view command. When users can specify pi format, the pi format argument was passed to utilize format description function. But inside it, the error handling was wrong. If it received an invade format value, say pi format count, it will return null pointed. Then the null pointer dereference occurs and crashes the process. This bug is unlikely to exploit but can cause an DOS on the hypervisor. The second box was the one we used to construct the exploit, CVE 2019-1A3A9. This is a heap-based buffer overflow bug. We have this resource create comments. All arguments can be controlled from the guest machine. When the byte argument is set to Virtio byte custom, we can control the size of buffer allocation. And we have this resource inline write commands. As its name suggested, we can write content to the resource buffer. It first looks up the target resource by its handle ID and perform boundary checks. If the checks pass, the content will be written into the resource buffer. However, the crash form fuzzer tells us that these two boundary checks can be bypassed. To help you understand this box, I will use some graph. First, we send a create resource command, creating a buffer of size of 10. Then we send a resource inline write command with the data of 108, but we change the W argument of this command to 0x8000. This will make all 108 rise to the resource buffer, which is clearly a buffer overflow. This is actually an integer overflow problem. The code will consider the 0x8000 as a negative number and then bypass the boundary checks. Let's talk about the exploit development. Another approach for using lib protobuf notation is you can easily dump the arguments that leads to a crash. And we can construct a POC from the crash dump easily. Just fill in the arguments and invoke the aforementioned API is enough. But a guest-to-host exploit requires us to trigger this from the guest machine. That means we should figure out how to invoke the vulnerable APIs from inside the guest machine. As you can see from the graph, our target is in DP's red color, and we need to reach here from the guest side. Now we have two options. The first is to build the exploit from the userland. It is easy for debugging, easy to ship the exploit and launch an attack, but it involves more aspect layer. The second is to build the exploit as a kernel module. It involves fewer aspect layers, but it is difficult to debug, and some latest version of Linux requires a signature to load the kernel module. We definitely don't want that. So we chose the first one. Here's a larger picture of the stack, making our all interfaces in blue color. Let's start from the bottom. We have the Virtio renderer API, which is also our target. The backend module calls these APIs to process rendering tasks. And between the front end and backend, we have Virtio API. This is the bridge between guest and host. Inside the guest, we need to submit the comments from userland to kernel. But what interface is involved here? After some research, we found a library called libdrm. It provides a userland interface to interact with graphic cards. Then our problem is finding the APIs from libdrm, which is corresponding to the vulnerable APIs of Virtio renderer API. It turns out they can be triggered by I/O control with specific command types. Then we can construct the POC for guest machine. First, open a graphic card FD and then simply use DRM I/O control to submit the commands with malicious arguments. When we compile this and run it inside a guest machine with Virtio GPU setting, the QEMU process on the host machine will crash immediately. Now we have a heap overflow POC with almost no constraints. We can write arbitrary data with any size. This is a powerful attack primitive. But several questions we need to solve to reach a guest-to-host escape. The first question is what content we want to overwrite. Thus, we need to bypass ASLR. Because of address layout randomization, the memory layout is random on each boot, and information leakage is the most common method to bypass the mitigation. We tried hard and spent plenty of time on this problem, so this is considered to be the most challenging part in this research. Again, let's analyze from the stack. We see the Virtio API is the bridge between host and guest. So our first idea is to auditing this interface. We audit every Virtio output function on the backend, but did not catch any bugs. Then we expand the scope to other Virtio device, for example, Virtio Net PCI, Virtio SI PCI, and so on, but still no founding. Next step seems to be further expand the scope to other traditional device driver on QEMU to look for information leakage. But then I thought, wait, is it Virtio the only communication channel between guest and host? The answer is no. We found a slide from Virtio renderer developer on X.org Developers Conference 2018. It illustrated the process of rendering resources. This workflow indicates the resources is transferred through some memory mapping. And if we want, we can look for some uninitialized issue on second step. Maybe we can transfer some valuable information to the guest. And let's look back for resource create function. When you're allocating the buffer for resources, it uses manual function without any initialization. That means some buffer may contain leftover pointers inside. With this knowledge, we can update the picture. Besides the Virtio API, we have a backend storage mechanism between the guest memory and the host resource buffer. You can consider this as a special kind of memory mapping, and we went through the code to find the correct commands to map the resource buffer to the guest and request a transfer. Then we can use some heap manipulation technique to leak the address we want. The first thing to leak is Virtio renderer library address. We found this interesting structure called utilize hash table in the size of 0x20 bytes. It contains some function pointers from Virtio renderer library, and we want to read that memory from the get side. First, we spread these objects over the heap with create subcontext commands. Second, we destroy all the subcontexts, and these hash tables just allocated where we free to in the ptmalloc implementation of glibc. This buffer will go to Tcache bins and fast bins. Third, we allocate resource with buffer of 0x20 size, so the resource buffer can occupy utilize hash table buffer we just freed. Then we transfer the host resource buffer back to guest machine, and finally we can read the compare function pointers from the mapped memory of guest machine. We also want to leak a libc address. This is even simpler. We can just allocate some resource buffer large enough, say 0x1000. libc will allocate such a large buffer from the unsorted bins, which contains pointers to the libc address. And we transfer this buffer back to guest and read out the libc address done. So the first problem solved. The second is where we want to override. The exploitation of heap overflow usually requires some heap layout manipulation techniques. So we can override something useful. We first use heap squaring techniques through a number of VRAM resource objects on the heap and observe the heap layout like this. First is the VRAM resource object with ID of X, then comes its buffer, and we have a series of small objects of 0x20 size, which is some hash table related structure of resource X, helping to look up the resource object with its ID. Then is the VRAM resource with ID X+1 and its buffer. When we saw this layout and attack banks came out, we can overflow the buffer of resource with ID X and override the content inside resource X+1. If we override the buffer pointer to somewhere else, then we can perform another transfer inline write operation on resource X+1 and get an arbitrary write primitive. But this will ruin the hash table structures below resource X buffer. But that's okay because they are only used to locate the resource X, and we don't need to touch it anymore when we have an arbitrary write primitive. We've turned a heap buffer overflow into an arbitrary write. Next, we need to hijack the control flow. What we want is a writable global pointer in Virtio renderer, and we can trigger it free. We found this called resource unreferenced function. This function will be called on each destroy resource operation, so we can use arbitrary right to write this pointer with system function from the libc and set the headers of x+1 resource to arbitrary comments we want to execute. For example, the comments to put up a calculator allows we perform a destroy resource operation and the comments will be executed. Here's the whole picture of our exploitation. Now let's see a demo of this exploitation. We start the virtual machine now. We copy our exploit into the virtual machine and SSH change it. Now we execute our exploit. And the calculator will pop up on the host machine. At last, here's some takeaway for our talk. The first, reforming a common parser to structure a word for third-party library requires many works, but totally worth it. And we talk about how to babysitting a parser. You should teach it export more code and run faster. And virtual device and drivers are good places to humble bugs to construct guest to host escape exploits, especially the graphic proceeding module. The parallel virtualization also points to such an attack, especially when it involves third-party libraries. So this is the end of our talk. Thank you.